Thanks. Yeah, as I said, I'm very happy about the invitation to speak at the Journées Arithmétiques. It's a pleasure. I would have loved to be with you in Luxembourg, but I was just traveling too much the last few weeks, and I realized I need some rest. I'm sorry. So I want to talk about a small paper I wrote called Wild Betti sheaves. And so what is this paper about? So in algebraic geometry, there are many different sheaf series. Or like in corresponding cohomology series, which in many ways behave quite similarly, but in some ways don't. And I want to focus on one way in which there's usually an asymmetry here. But before explaining this asymmetry, let me recall some key examples. So one is what's usually called the Betti setting, and which is the one that I will focus on in this talk. It's probably the most classical setting. So in this case, maybe we have a variety x over the complex numbers. Variety meaning, I don't know, separated scheme of finite type or something. And to this we can associate, well, it has some the complex points, which are a nice locally compact topological space. And you can take its singular cohomology groups, which gives us a Betti cohomology series for these varieties. And you can also introduce the category of Betti sheaves, which gives you a sheaf series. So can look at just sheaves on the complex points of the topological space with a being, in the being groups or in the derived category of the being groups, something exists. So the derived category of the being sheaves on this topological space. And I will probably think infinity categorically, although it will probably not, well, maybe at some point it will matter a bit, but I try to remember to write big. Do interrupt me if I get too small. So in particular, like in any sheaf series, there's a constant sheaf or structure sheaf 3x, and you can get cohomology groups just as a, I guess it's in some sense it's the xi's in this category of the unit objects. So any sheaf series gives you a cohomology series just by looking at self x of a unit. Right, so there's one sheaf series. Another classical sheaf series is D modules. So there's this Riemann-Hilbert correspondence, which relates local systems on such an X to vector bundles with an integrable connection, and more generally some kind of singular constructible sheaves can be related to more general kinds of D modules, the modules over the rings of differential operators. For simplicity smooth variety, x over k, where k is the field of characteristic 0. We have the ring Ex of differential operators on X, or the sheaf of rings. And you can take the derived category of modules over this sheaf of differential operators. And a third example is the etale setting. So again, here we have varieties for some field K, and we pick an auxiliary prime L, which is not equal to the characteristic of K. So for example, if K is characteristic 0, we could pick any prime, but I will also particularly be interested in the case of positive characteristic P, but then L should be not P. And then we can take this thing usually called something like d-ad of X with QL bar coefficients. So analytic sheaves on it, analytic etale sheaves on X. And there are probably many slight variants about the precise definition of this, but it will not matter for this talk. I shouldn't put this too far up. Sorry. I shouldn't put this in the shadow. Right. So these are three sheaf series giving rise to like Betti cohomology. In this case, you would get the Rahm cohomology. This is what's computed by these D modules. And in this case, you would get etale. So in any sheaf theory, there are certain operations you can do. So there are always there's this yoga of the 6 functors. So in any such sheaf, category should have a symmetric monoidal tensor product with an adjoint, which is internal Hom. So whereas this is in some sense the left adjoint of this one, so you should always, when you have a map from X to Y, there should always be a pullback on sheaves with the right adjoint, which is a push forward and computes cohomology. And also there should be this cohomology with compact support having a right adjoint, this exceptional inverse image. And a lot of interesting stuff about sheaf series can be purely phrased in terms of those 6 functors, and not many cases then can sometimes be done independently of the specific cohomology theory because it's all just the yoga of these 6 functors. But there's one thing, or where there's some kind of asymmetry between some of these settings. So roughly speaking, some sheaf series are tame and others not tame, I will call wild. Where one way to think about what tame means is that all the local systems, all the invertible, all the local systems on an affine line are trivial. I mean, I don't want to give a precise definition of what I mean by tame, but in practice, I think this will do. So you would usually think of the affine line. I mean, the Betti realization is just the complex numbers. It's contractible, and so any locally constant sheaf must necessarily be trivial. But it turns out that there are some sheaf series where not all local systems are trivial. So let me give some examples. So the Betti setting is tame. The D-module setting actually turns out to be wild, even though you might think that the Riemann-Hilbert is closely related to the Betti thing, but there is some important caveat about Riemann-Hilbert. So why is it wild? Here's an example of a non-trivial local system on A1. So what does it take to define a D-module on A1? So the ring of differential operators on A1 is just, well, you have your coordinate x, and so you certainly have polynomials in x in your ring of differential operators, but you also have differentiation against x. These are, maybe I shouldn't write a polynomial algebra. I mean, these do not commute, but the commutator between the two is plus or minus 1. I never know which way commutators go. So they don't quite commute. But in any case, to write down, and so then D modules are really just modules over this Weyl algebra. And so what's the example? So you can take just the module, which is free on a symbol called E. And the idea is that E is the exponential of x. But of course, the exponential of x doesn't make sense as an algebraic function. But still, we can determine what the operator nabla should be. Namely, it should send, well, the exponential is somehow characterized by mapping, by not doing anything to the exponential. So E just maps to E. And then you can uniquely extend this to any polynomial. So I don't know. So if you have some f of x times E, then just by the Leibniz rule, this must go to f prime of x plus f of x times E. And so this is because it's just as a bare module over K John X. It's just free of rank 1. This means it's a local system. But it's not trivial, because if it was trivial, then this would mean that you can find a solution to this differential equation, nabla of something is equal to something, or minus something. But this cannot be solved in polynomials, because the solution would have to be the exponential. Local system. But non-trivial. As f of x. How does it work? A related fact is that, I mean, if you somehow embed A1 into P1, and we have your d module M over here, and you have some of the complement infinity, then M has an irregular singularity. And infinity. In fact, the Riemann-Hilbert correspondence will tell you that if you have a D module with the so-called regular singularities, then it would always correspond to a Betti sheaf, and Betti sheaves are all tame. And so if you restrict to D modules with regular singularities, they are tame. So you can also build a sheaf theory of D modules with regular singularities. They're stable under all these 6 operations. And this would be a way to turn a wild theory into a tame theory. And finally, let me also explain what happens in the etale case. So here it depends on the characteristic of K. So if the characteristic of my base field is 0, then it's tame. In fact, in this case, the theory of etale sheaves is very, very similar to the Betti setting. On the other hand, if you do this etale theory in positive characteristics, then again it's wild. And so what's the example here? In this case, the example comes from the Arithmétiques cover. So in characteristic P, there's a cover, a non-trivial etale cover of A1. So A1 is somehow not simply connected in the etale setting in characteristic P. Instead, you can find this cover of A1 by itself, where it sends a Y to x, which is y to the p minus 1. And then because, I mean, to check that this is etale, you somehow have to check that there are no common zeros of the function and its derivative. But if you take the derivative of this function, then there's a factor of p coming up front, that p is equal to 0 in our base. And so just the derivative of this function is actually just identically minus 1. And so in particular, there can be no zeros to the differential, and hence it's everywhere etale. It's actually covered with structure group FP. So it's actually turns out that this is really this is compatible with addition again by this Fermat's little theorem, and the kernel is precisely all the y's where y to the p is equal to y, which is precisely FP. Well, this doesn't yet quite define a local system, but it's easy enough to turn it into one. If you pick a piece root of unity in our field of coefficients, Q bar cross, then we get this character this additive character psi, which goes from FP to Q bar cross, which sends any a to the zeta to the a. So think of this as x plus 2 pi times a over p. And so it's again some kind of exponential. And then you can somehow do a push out of this extension against Q bar cross, and then get some kind of Q bar cross torso, or in other words, a Q bar local system. Define some local system in this category of etale sheaves on A1. And it turns out that in many ways, this Artin-Schreier local system behaves very similar to this kind of exponential local system in the D module setting. Yeah, at this point, you might wonder what's better, tame or wild? And the instinct might say that tame is better because you have much better control over what's happening, and A1 doesn't have any weird fundamental group. But turns out that having these interesting local systems on A1 is also a virtue because they allow certain extra operations to exist. So. Namely, you can define something called the Fourier transform. So, which is turns out to be a really powerful operation on sheaves with many applications. So let me recall a little bit about this. Let me first do something very classical. So if just V is just a real vector space, finite dimensional real vector space, then the Fourier transform is an isomorphism between the Schwartz space on S and the Schwartz space on V dual. So these are functions on V with some rapid decay condition. Defined so that the Fourier transform taking any F2, I don't know what I want to call this, to the integral of f of V times x of 2 pi I dw dV. Just the usual Fourier transform is an isomorphism. And actually the same works and is actually much more elementary for V, a finite dimensional FP vector space. In this case, you're just taking all functions on this finite set, and you write down basically the same function, except here you need to pick a piece root of unity, but then it works. So I guess that's called the, what is it called? Finite Fourier transform or something. And then Deligne observed that there exists an analog for etale sheaves and characteristic P. And the way he found this, I think, by employing something called the sheaf function dictionary. Of Grothendieck. Namely, if you have any sheaf on X Q bar, where X is now defined just over the finite field FP, then this can be used to just define something numerical, namely a function on the FP points of X. The function of F from the XP points of F to Q bar. Which so whenever you have an FP point of X, you can pull back this etale sheaf on X to just the spectrum of FP, but etale sheaves on a point are just representations of the absolute Gauer group. The absolute Gauer group of FP has this canonical element which is the Frobenius and automorphism of FP bar. And so whenever you pull back to an FP point, you get a QL bar vector space with an automorphism. You can just take its trace. And in this way, the operations that you can do on sheaves upgrade more naive operations you can do at the level of functions. For example, functions you can multiply, which on the level of sheaves corresponds to tensoring the sheaves. Or, I mean, sheaves you can pull back, which on the level of functions just means like restrict functions along the map, or the push forward maps then correspond to some kind of integration along fibers maps and so on. So there's some dictionary. The tensor corresponds to multiplication. F upper star corresponds to restriction. And F lower shriek corresponds to integration along fibers. Or summation along fibers, because these are just finite sets. The radial joint functors are more difficult to interpret. But I'm going to give you extra stuff you can do on sheaves that you cannot easily do on the level of functions. What Deligne proved is that for V, again, a vector space of FP, dimensional vector space, that the category of etale sheaves on V is equivalent to the category of etale sheaves on the dual vector space. Via some combination of symbols that just mimics the way the Fourier transform is defined there. So here you're kind of restricting the function f of v to a function of v and w, then you're multiplying it by this exponential, and then you're integrating along fibers. And this tells you how you should mimic that. But one critical ingredient you need here is this exponential function. And this precisely comes from this Artin-Schreier cover. So we need this Artin-Schreier cover in order to get this exponential factor that we need in the Fourier transform. And the Fourier transform then, by construction, is compatible with the thing that you get on the level of functions. So if you have the sheaf here, you can take its trace of Frobenius, get a function, and also here, and this is compatible with the usual function theoretic Fourier transform. And this turns out to be an extremely powerful tool with many applications to many different areas of mathematics. So well, Deligne and then in particular Lemong used it to give a very slick proof of the wave conjectures. But also, it has lots of applications to analytic number theory. Because these functions that you get here often are certain exponential sums of interest in analytic number theory, which can then be analyzed using powerful techniques from algebraic geometry. It also has lots of applications to geometric representation theory, the Langlands program, and so on. And so for many of these things, you're really getting used to wanting to have such Fourier transform, and hence wanting to have a non-trivial local system on A1. And maybe just let me write down here. So the same works in D modules. but not in D modules with regular singularities, only in the fourth category of D modules. In this case, it's actually something rather elementary. Recall that a D module was just a module over the Weyl algebra. And basically, under the Fourier transform, the action of x is swapped with the action of the derivative, and the action of derivative is swapped with the action of x up to some signs. So you're kind of swapping what the geometric variables are and what the kind of derivative variables are under the Fourier transform. And also in D modules, there's lots of applications. By the way, maybe I can ask now, when should I stop? Should I leave time for questions, or just kind of speak until quarter?
Until quarter.
Yeah, quarter to. Okay, great. Thanks. Right. And so the question then that poses itself, and which I think was not yet systematically addressed, is whether any sheaf theory can be upgraded to one which does admit such local systems on A1, which has a Fourier transform. And in particular, must have a non-trivial local system on A1. So maybe I should say that if you just take a skyscraper sheaf at any point of V here, then the properties of this correspondence tell you that you must get a local system on V dual. And if you didn't pick 0 here, then it must be a non-trivial local system on V dual. So if you have such a Fourier equivalence, you must have these non-trivial local systems on vector space, in particular on A1. And the answer to this actually, yes. With maybe a very small caveat about precisely what I mean by sheaf series. So for quasi-coherent sheaves, I don't think this is possible, at least not without significant changes to the question. But in any kind of motivic sheaf theory, it is possible. And what I want to do in the last 50 minutes is to make this explicit. I don't want to give you the general recipe. It's not too difficult to write down, but I want to make this explicit in the case of Betti sheaves. So we want an enlargement of I mean, you have sheaves on X with coefficients in rough category of Abelian groups. So you want to enlarge this into something called it just wild sheaves on X, so that there is a non-trivial, some kind of exponential local system well, on C or just really on the real numbers on X equal to R. And the best case, and this will actually turn out to be true, is that we have some enlargement into some larger symmetric monoidal category of like coefficient objects, enlarging just being graph category being groups. W for wild, so that wild sheaves on X are really just sheaves on X with coefficients in this bigger category. So really just enlarging your coefficient category, but then just still consider usual sheaves on X. You would usually run into this issue that this doesn't work. So usually, so in practice, most categories one considers are compactly generated. And so then up to some small issue, basically just the derived category of some ring A. So usually if one tries to build some enlargement, you usually end up just with rings on some module or maybe quasi-coherent sheaves on a stack or something like this. And it turns out that doing such a small modification will never get rid of this issue that you have no non-trivial local systems on the real numbers. Because this argument that the real numbers are contractible is really quite robust. So this cannot work. I don't want to give you the precise argument, but here's the idea. So any real number, so if you have this non-trivial local system, this kind of wide local system on the real numbers, then for any real number, the fiber of this at R must be an object in R that is itself some kind of free of rank 1, or locally free of rank 1 object, invertible object. So it's among the Picard group of W. So you get a map from R into the Picard group of this category W. And it's just usually the case that if you have some kind of, it must be somewhat continuously varying, because we somewhat started with a sheaf on the real numbers. So the continuous family of invertible objects in W. And in kind of an algebra, you usually cannot have a continuously varying family, like on the real numbers of Lagrange bundles. On no algebraic variety is like can you ever have such a map? So it does not usually exist. But still turns out that there's some universal example of a W that does work, and the definition is the following. He's a presentable, stable, arithmetic monoidal, so they have a tensor product. Technically speaking, I should say presentable, stable, infinity category of completely and continuously R-filtered objects. R-filtered objects. Of the derived category for being groups. i.e., a chain of objects fill R M for all R. I mean, some kind of ascending filtration, such that it's on the one hand a continuous filtration. Complete was in front. That's my first condition. So in general, filtration is complete if the intersection of all the filtration steps is 0. And it's continuous if any filtration step is determined by the filtration step slightly further along. So it maps isomorphic to the limit over all R prime strictly bigger than R of the filtration step. R prime. Oops. And And there is some kind of canonical way to put a tensor structure on this in the usual way tensor filtrations. And so, for example, the unit is something I will call the 0. So this has fill R Z0 equal to Z if R is greater or equal to 0 and 0 when R is negative. So for negative R, at some point should get 0, but at some point then from 0 on you can put Z. But more generally, for any real number, you now get an invertible object. Namely, you get Z of R, which has fill T of Z of R, or let me say T and R. We have a ZT, whose R's filtration step is Z if R is greater or equal to T, so only at time T this appears, and before time T there's nothing. And so this is an invertible object. And it turns out that some of these are precisely in this way the fibers of a non-trivial sheaf on the real numbers. Let me just end with a theorem summarizing the main properties. There's a Z of T. The fibers of an exponential local system L on real numbers. I mean, in general, like sheaves on the usual sheaves embed into wild sheaves, which I define to be sheaves on X with coefficients in W. Fourier equivalent solves. What else? This is actually not new. This notion was previously defined by Tamarkin in a slightly different formulation. So this recovers a previous construction of Tamarkin. Which has found applications both in symplectic geometry in relation to Fukaya categories and in the study of the irregular Riemann-Hilbert correspondence. The latter thing shouldn't be too surprising from the perspective of this talk today, because on the irregular Riemann-Hilbert correspondence, you're trying to extend the Riemann-Hilbert correspondence to irregular D modules, so to the wild setting, and then clearly you need some kind of wild sheaves also on the Betti side. And this construction of Tamarkin was used for that purpose. And maybe the new observation is only the following. That in some sense, W is universal with respect to properties 1 and 3, so that you get a new exponential local system defining a Fourier transform. Up to one small issue is that you could have defined a version of W where you just swap the order of the filtration and you. This gives another example, but those two are some of the universal case. And this actually has some kind of weird consequence that in some kind of weird sense of generalized algebraic geometry, you can try to make sense of the spectrum of any symmetric monodal category. And well, as everything, this lives over spec Z. And there's an action of the positive real numbers here by rescaling the filtration. Multiplicatively the filtration. And it turns out that this is in a suitable sense, this is a torsor for the positive real numbers over spec Z. It follows quite easily from 5 if you read it carefully. And so this somehow means that in this somewhat slightly generalized sense of algebraic geometry, where you're allowed to take spectra of any symmetric monodal sensible stable infinity category, suddenly there is a very interesting torsor over spec Z for the positive real numbers, which gives you a completely new way to localize in algebraic geometry. All right, let me stop here.